me. Maybe you have a translation. Okay. Thanks for this opportunity. Always interesting talks with this group. Hopefully, also today. Okay. Few slogans. It's let's say opinionated, but still we're in the realm of machine learning, so it's 90% precise. Okay. So yeah, AI changing the way we do software, changing the way we explain to the machine what to do. Okay. So NG knows NG. I just wanted to please raise the hand. Okay. Generally, you may help me if you wish. Okay, thanks. Okay. Scaling computation. Recently, a couple of years ago, we finally actually estimated the number of the connections of the brain. It's actually not a trivial problem. We thought that it has almost infinite number of connections, but it's not actually. It's approximately 10 to the power of 15. Okay, so it's not that infinite. Okay, so statistics is finished by 2015, and it says we have 100 billion connections. So it's approximately to the number of neurons. So we have to raise only 3 orders of magnitude to arrive to the number of connections of the brain. Okay, so it's not that impossible. But okay, neurons are more complex, so let's add 3 more, like to have a complete module of the neuron, human neuron. So 6 orders of magnitude. Okay, so maybe some quite recent we can arrive to this scalability. Okay. Fighting about the robot future. Okay, I like that doodle. There was this discussion a year ago between Mark and Elon about AI. One says, okay, we have to regulate AI. The other one, don't be so pessimistic. And the problem is that actually. The part I worry about when actually AI is still stupid, so it can be used by, let's say, any not very intelligent people to harm himself and everybody around. Okay, so yeah, that's not when the AI become the self-aware. Probably it will be a very nice person to talk to. Okay. This is a famous slide from NG course on Coursera, why deep learning, let's say, explode as a solution. So, yeah, until you have a small training set, more or less any approach is good. Linear is fine, it works. Okay. Maybe some non-linearity just in case. When you have a large amount of data or complexity grows and the data become very scrambled, then it's very hard actually explain how the data are organized. We will see later the specific words. So actually the black box solutions, as a neural network is working better. Okay. So it does much better. So it's for certain tasks it's superhuman. So okay, the main applications are in this. It does this. It maps inputs and outputs. Okay, so it calls supervised learning. So we control the how tasks should be solved. Okay, there are another much more open discussions whether based on supervised and reinforcement and so on and so forth. it's actually okay. Another way to state the task, and but what let's say the business is done with this. Okay, so we know it's working. We can test it. We know how to test it, and we can assure that it's. If we need 99%, we can achieve with this. Okay, maybe quite costly, no? But we'll discuss later. Okay. There are plenty of, let's say, it's very rich, this area, okay? And so it's supervised and supervised reinforcement learning of, I will do, how was the last, okay? All my knowledge is of this realm. So classification and image classification. I will use this image classification because it's very let's say representative to classify cats and dogs, and it actually covers all the. It doesn't have limits of the complexity. Okay, but it solves a lot of very meaningful problems like fraud detection, like customer segmentation. A lot of money is done in these areas. Okay, another slogan, but it's still it works quite well. Rule of thumb, no? That if the person can do this task in 1 second, probably it can be automated. Okay, or if you can separate somehow the set of tasks on the number of tasks by human 1 second task, that probably can be automated. Okay, it's an old slide. Data is new oil. We actually understood it before deep learning started. There was this kind of feeling, actually. Okay, what type of data sets? Different types. As I told you, I live mostly in images realm. So here's the particular data set, which is a multi-label. So it's actually describes, the network describes what it actually sees. Like here, container ship, amphibian, lifeboat. Okay, so it kind of tries to give more, let's say, synonyms to describe. Okay, the face recognition is absolutely ubiquitous now. Then text analysis, NLP. I'm not absolutely expert in this. A little bit of time series I did in the past. Recommendation systems, speech and music. Let's say recognition. That's also in our pockets. Okay. Source of data sets is there. Plenty of, I didn't put all of them, but the main is Kaggle. Who knows Kaggle? No? Okay, good. Okay. It's a good way to start. You can see the solutions, you can see the problems, how they solved. You can actually probably find a solution to your problem. Okay, already solved. Okay. What we will not discuss. Okay, modules, how to structure modules and so on. We won't discuss how to train them. We won't discuss how to deploy them. We won't discuss how to do embeddings, how to associate between different. We won't discuss how to do clustering. We won't discuss how to deploy and how to build the hardware for the deployment of. Maybe for the next talks as well. Okay, but I wanted to discuss the. It's already not novel, but it's still a couple of years ago. One guy, Karpathy, proposed this, coined this software concept, and it actually fits quite well with the things we are doing in AI. So we said, okay, Software 1.0 is you get an idea, okay, then you describe it as a logic, then you build a data structure, and you write a program, okay. So explaining to the computer with instructions. Instructions are very well described. It can be a statistical methods. It shouldn't be anything very like if-else statements. Okay, it can be much more complex. And there is another realm. You have. It can be absolutely the same idea you want to solve, but usually it's not. Okay, you can do something more usually. Okay, then you build a data set, and then you ask some black box, which is usually a neural network, to figure it out how to solve it. Okay, and as an exit, we have this graph of connections that somehow encodes all the information that you put inside. Okay, good and bad parts. That's a problem. Okay, shit in, shit out. Okay, so no magic. Okay. So what the heck is Software.0? Okay, so is a I wanted to show first this, then that. Okay, sorry. What the hell is Software.0? Is automating the ineffable. This is ineffable is coined by Casey Kozyrkov as a decision intelligence at Google. Very strong woman, okay. And become more and more stronger in AI. So what is ineffable? For me it was a new term, but after all I discovered so it's Latin, so indescribile. It's impossible to describe with words, okay? So if you want to automate something, like how we distinguish cat and dog from images, how you cannot describe it, but it's easy to give an example. And let some black box to figure it out. Okay, it's a very complicated and good question how to build this black box. But we know that if we did mathematics, now there is this kind of basis functions, and you can approximate any function with given this set of basis functions. If you know Fourier transform or any other wavelet transform and whatever. Okay, so we know that there is a way you can represent whatever input to whatever output. You can even represent complete noise, random noise. It's not that. Neural network can learn noise, and it will give noise as an output. It's not because neural network is a one way of basis functions, so it can represent this type of inputs. Okay, so and recently, not actually recently, CNN was invented in the 80s, but there is these architectures that are very efficient, and a lot of interesting features that actually can solve this problem. Okay, there were these I don't know who knows who studied. Me also, I was laughing when I studied 90s when people were doing neural networks. We were laughing at them. I did mathematics, applied mathematics, because we knew that it will not work. Okay, and now I'm said, okay, maybe I should have not laughed so much at that. Okay, there was this kind of. It is still a problem. So to give to machine, figure it out. okay, to do the job for you. What type of job? Is to find the features, to find what actually distinguish cat and dog. We still don't know actually what distinguishes them. The machine, if you give a representative dataset, enough representative dataset, it will figure it out. Okay, but it still can do. You have to control it. You will feel you solve the problem, but quite often you don't. Okay, the pipeline, I split it because it didn't fit actually in. There was this image in some journal I liked how the neural network work, and I said this is pipeline for the image recognition mostly. Okay, this is exactly for image recognition. So we have a training procedure. Where you build a data set, you give this data set to this black box, and it figures out how to distinguish between dog and cat and any other animals. Okay, and there is this we call it inference or testing pipeline. Okay, that network is consists of multiple layers, if you remember, and in particular, they describe here how mostly CNN, convolutional neural network, works. Okay, so if you, it's a long story how a convolutional neural network works, but it kind of filter that applies to whole image, and it kind of is a funnel. So every layer, it tries to reduce the dimensionality of the input, but increase the, let's say, the abstractness, increase the level of understanding of the input. Okay, so in the first layers, it is known that the image looks for the small details of a few pixels, like how few pixels of the image is connected. So if you have a gradient, so strong change for so it's like a step function, no? So it's white, black and white. So it's a strong gradient. So it's probably an edge, okay? Like an edge between this white and this black, okay? Then on the next layers, and it reduces dimensionality. So it's from 4 pixels returns 1 pixel. Okay, so it's actually it's a projection. Okay. Then there is this non-linearity that is still important because the convolutions by itself is a linear. So linear function cannot learn much. Okay, you have to introduce something non-linear. So it's activation function of the neuron. That is non-linear by definition, otherwise it won't work. And it starts learning bigger pictures, like a noise, like a connection between different parts of the, and so on. And then at the end it classifies, it returns kind of a distribution of the, how I feel what this image is. So it will never, it will never tell you that I'm 100% sure. Even I would say the contrary. If the network says I'm 100% sure, you'll be suspected. Something works badly. Okay, you'll suspect that no, I don't like it. And actually, it finds, you see, a 10% wolf. And it's a similar concept. It's still an animal, and probably the dogs and wolves has much in common. Okay. So, what is typical software.o code? Okay, green is our, let's say, software 1.0. Okay, and red is the software .o. Okay, so. The input in this case is the person represented, let's say, as an image, the photo of the person. Okay, and this is a simple string, is a label. Okay, so and the action of the let's say neural network is actually to reduce that very huge input to this particular label. Okay, so there should be some mechanism of learning from what different types of input as an image to the labels. Okay, and it opens me a door or sends me to search someone else. Okay. So this is let's say just a pseudocode I invented, but this is a real working code. It's complete. It's complete. Once you install all the supported software like TensorFlow and all the stuff, Keras and so on, you download all data sets. You can run this code, and what it does, it will train a module to classify digits. If you have heard about MNIST, the dataset of the digits, it's a hello world of AI. Okay, so this is the part of the where you describe actually the architecture, how it's composed, of what layers. Okay, this is the preparation of the module. So you still give some instructions how you optimize it, which algorithm it will use, what loss function, what metrics to track, and so on. Then all studies, all PhDs in the recent 5 years stays in that single line. Okay, the magic happens there. Okay, and so. It will, that figures out. That what does. Once you train, you obtain the weights. You need to process, evaluate this network. So infer, it's actually one line code. Once you will stay much more time, much more lines to prepare data rather than to process it. Okay. Okay. So. I tried to map concepts from software, classical software. Actually, it's not a map. It's actually the same thing that simply applied to different set of inputs, I would say. Okay, so in this case, the logic that we represent as a block scheme in our software in software.o is the data set. Okay, so as Karpathy wrote here, the program of the software.o to O. He does nothing that work with dataset, like message dataset, like label it, unlabel, understand data, and prepare that data to the machine. Because there's nothing. Everything that is the machine will know is coming from this from the input Okay, there is some little bit work and so on, but. Okay, then you choose a programming language how to solve that that logic that you wrote down on the paper. Okay, so the programming language in software.o is a topology of neural network. If you want to solve the image classification, you choose one topology. If you work in NLP, you choose the other, and it's actually not that strict. You can use still the modules done for that works well in image recognition, also in NLP, and it's interconnected all together. And then you have to. The hardest part is to find the loss function. Okay, so how you actually what do you optimize? What do you try to reduce? Okay. So that architecture returns the values, but unless you give you sum them up, you kind of like reduce to the scalar, to the single digit, you won't do much of the optimization. Okay, so okay, half of works I would say dedicated to the architectures, half of works of finding a new loss functions for different problems. Okay, so we choose the programming language. We use this architecture. We use here's the cross entropy loss. Is quite extremely used this loss function. Obviously, no one programs them. You just import and then you give an input and it returns the data. Okay, then you compile. Okay, so the compiler in software.o is the gradient descent and backpropagation of error. Okay, why it's a compiler? Because it produces finally a machine code which is the weights in software.o. Okay. So, is it too cryptic for you? Just tell me. Just ask. Okay. Okay. So the gradient descent is find the minimum, maximum, doesn't matter, of the function of the cost function. Okay, of the loss function. Cost. We can call it cost function, loss function. Okay. And it's still not trivial problem because here's an example, very slow convergence due to this very narrow valley. Okay. Then the backpropagation is the way to update weights. Once your network returns something, you have to somehow learn on that, on errors, or give a benefit when you predict it correctly. Okay, and then it produces weights. Weights is a numbers. I use this visualization. It's quite nice. There are different software that visualize weights. Okay, you can always work. You can always read the machine code. No, you can analyze. You can understand. You can disassemble it. You can understand what actually the program does. It's very, very heavy. So it's also in this, to analyze weights is a heavy task. Okay, you still can get make a statistics and so on. What is weights is the let's say how they learn to solve your particular task. No, you can see the dogs being given and the neural network that's so-called generalized. You see some maybe similar to noses, faces of dogs and so on. This is so it's not the face of the dog, if not the snout. Here's not the clouds, but maybe fluffiness. So we call it like it learned partially a concept of fluffiness. Okay, so the clouds, what is it? It's something fluffy on the gray or blue sky. So you see the presence of blue here, fluffiness and so on. Here's the buildings, okay, different type of buildings. You can recognize this type of, and it's a pure visualization, okay. So weights been taken and they've been represented as an image, okay. So it's not a real what is actually is inside network. Okay. Then once you have machine code, you want to understand how well it performs. So it's testing. Okay, and it's the same testing here. We have loss curves and training curves. Loss curves actually shows how well our network learns. Our module, let's call it module. It shouldn't be a network. Learns, and then how actually well it performs. There are these different representation of the metrics. Okay. You see, you can draw these curves, and simply, the more it tends to this perfect classifier, the better it is. Okay. Okay. There is this kind of joke in classifier. Now, I have a classifier that is 60% accurate. No,
it's actually a shit, because the random classifier is 50% accurate.
Okay. 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 Then you have bugs. What are the bugs? This is a real from our system. We do. Okay. This is a module, an ensemble module that does the detection of the extraction of the skeletons from the human body. So you see that there are two people, one hanging with another, and the module tries to understand this food or whom to it belong, and so on and so forth. For example, we have these concepts of false positive, false negative, hard negatives, and another other falses and true positives, and so on. For example, I don't know if you're familiar with this. Is mostly from the statistics. Okay. It's an errors. Okay, a different type of errors. For example, here the network somehow saw two people. Okay, it drawn the skeletons. Okay, here what the error is, the network couldn't see the person. Okay. So, okay, let's call it false positive. Here's the false negative, so it didn't predict when it should. Here it predicted when it shouldn't, okay? Here you see my leg is actually, the network is, let's say, drawn me a leg that is 180% rotated backward, taking the foot from the other guy. Okay, so we call it hard negative, but it's so it's even for the human is a hard. Okay, just to draw it how they actually the orientation of legs is here. Okay, represented. Okay. Okay. Then you want to understand why it happens when the false positive. So you do debugging. Okay. How you do debugging with the software? It's a lot of pain, but you still do. Okay. So we have this. There are much more instruments. The classical one are confusion matrix. So when the network confused with something, it actually very related how to our mind is confused. Okay, but let's see. Here's actual 2, and here's predicted. The network predicted 1. Yeah, it's not that far from 1. It could be okay, or actual 6 predicted 1. Yeah, someone badly written 1 maybe. Okay, or it's not a good example, but if you analyze MNIST, actually here network predicted 0. Probably it learned some concepts of being something circular, so it's 0, but it's not 0. It's okay. Another instrument I already showed that. Yeah, good way to visualize weights. Because if you, okay, this is a very nice weight, no? If you see the spikes, so your visualization, you like see everything white or everything black. That means some neurons like neurons are like going to the star and everything. So network learned nothing. Just it could be something in your dataset. For example, network may learn. For example, you create a dataset of images. I always speak about images because it's the only thing I know. For example, there are cats and dogs, no? And you say network. This is a cat. This is a dogs. And occasionally, cats make a photo by one cell phone and dogs by the other cell phone. Okay, only by these two cell phones, iPhone and Samsung. Okay, cats iPhone, dogs Samsung. Network what will do? She's lazy. It's lazy stuff.
she will learn to distinguish between two fonts and not to distinguish between cat and dog. Okay. It will be 100% accurate, but it will never, you will show an image done by another phone, it will say, I don't know what it is. Okay. Okay. What about bias? Now, what about all these problems like gorilla, man, and all this stuff? So you simply, you work with your data. So you do testing, you see the network learned badly from these curves. No, you do debugging. So you do this. You try to change, try to understand what model suits better. Try to understand the dataset. No, the dataset is a program. Okay, in this case, the dataset. So I repeat. Okay, so software.o it is strange. So it's a set of weights, but it's produced by the classical software because training software is a software classical software. Is just this code is a software any programmer can understand. Okay, once you know what is keras layer and so on, all the stuff you don't have to have a PhD to understand what this software, what it actually does. You probably have to have. Okay, and how to there is this is still a kind of craft. Okay, it's crafted software, so it's still craft. So if you if you don't place these, probably network will never actually learn. But where do you need to place it, here or before or after? What actually the parameter you should put on dropout? This is still a craft. It's not. It's a emergent science, but it's still quite often it's a craft. Okay. So let's debug a strawberry. Okay. So I picked it from one nice article. Okay. So I don't know why they put first neurons 45, then 31. Let's look at the 31 neuron. Okay. So we see the activation of the neurons. It learns some strawberry. Okay, input strawberry. Okay, some bumpiness. No, you see some bumpiness. So no sense what those images are. Those images. So those neurons are activated on those images. Okay, so at the neuron 31, some bumpiness been learned. At the neuron 45. Some bumpiness. Here you see all type of like insects, like something mechanical, something biological. Here it tends to be more biological and more round-shaped. Okay, so a little bit more global features been learned. Okay, then at the neuron 197, it starts learning even the shape, global shape. You see this, I don't know. In English, how to call it, knitting something. Okay, still bumpiness is present, so it's a very prominent feature. Anything bumpiness, so it's actually be suspected to your network. So you can show them all. One of the examples of these images, you may risk that your network will predict the strawberry on the mushroom. Okay, so it's a bumpiness is too much learned. Okay. And then let's say last neurons I learned the global features. So bumpiness plus geometry. Okay, so this is probably how the fruit. Jackfruit. This is probably a jackfruit. You see even the dog. See the form of the face. It may somehow it looks like being intelligent, but it's. Let's say truth. Unless software.o, there is this kind of saving. Let's say possibility. How much time I have? Maybe I talk too much. Okay.
5 minutes.
5 minutes, okay, perfect. So you give this, it's deterministic, okay? It is based not on deterministic concepts and so on, but if you give the same input, it will give the same output, okay? It's nothing living inside, okay? So nothing changed. Nonetheless, there are maybe another topics of the another system that actually learns and changes its behavior. You've seen as OpenAI games and so on and so forth. Yeah, okay. That's another thing. Okay, let me conclude with the pros of software.o. So it's computationally homogeneous because the operations are very simple. It's a matrix multiplication. Whatever system can do matrix multiplication, and it's very easy to implement in hardware. Okay, so it's simple to make it in silicon. Okay, constant running time, so forward pass of the network. If it does 100 milliseconds, it will be always for every image, every complexity of the image. It will maybe produce a sheet, but it will be constant, so it's predictable. Okay, constant memory use. If it uses 8 gigs of GPU, it will use 8 gigs of GPU. Okay, it's highly portable. You just take weights and then architecture, and you give it to any other developer, and he can use this module. They're just 2 files: one big file of weights and a small file of the architecture description. And sometimes it's better than you, okay? You okay on some tasks, okay? Okay, on the contrary, what is cons? It's large networks, but very hard to tell how they learn, how they work, okay? So, if you prefer to be transparent, so to be predictable and clear, so you have to stick with the 90% accuracy. So probably you eliminate that black box from your application. If you need a 99 accuracy on a difficult task, you have to go with the black box. But I also still recall the Cassie, she told a very nice phrase, like, but what's the problem with the black box? No, in this case, what the most mystery in the universe is how brain works. So it's by definition a black box. So you don't have to trust the people. Okay, if you don't trust the people, you have problems. Okay, okay. So yeah, but. It may fail in that the problem is actually not to trust the black box. The problem is to know how it fails, okay? And the networks may fail in an intuitive way, okay? So if the person fails, it will kill everybody and it will be intuitive, okay? So we can work with that, okay? If the network fails, we don't know how it fails. It is something strange and all this stuff, okay? When not to use the machine learning, I don't know, I'm sorry, another Russian guy. Okay, every decision of the system, every decision of the system must be explainable, so you don't use the black box approach, okay. The cost of error is too high, you don't use, okay. Then still it's discussable with or opinionated with autonomous driving. Okay, kill people, not to kill people. What's okay? And also getting right data is too complex or impossible. If you study, I don't know, something very rare, or for example, in medical applications, there are few experts in the world, so you cannot build the right, but you still can do, okay, usually, okay. Or you can describe, create a huge lookup table where every record is the solution, okay, so you do that. So, what the future? Okay, so anybody saw this? Know this image? Okay, is a Connectom? You have heard about the project of Connectom? Okay, is the project to map all connections of the brain. Okay, so simply to map. Okay, we don't have even not even to understand how it behaves. So it's a simple visualization of the all connections of the brain. So what is the future? Okay. Sometimes do we need? Okay. The question is. Some statements is learnable, so they may be learnable, but some statements we don't want to be learnable, like this if. I don't want to be inferred from data. If it's not, I don't want to let in. There should be zero probability that I can get in, okay? So sometimes we don't want to be something learnable. For example, if a person on the street stop, not like maybe stop, maybe not, maybe kill, no, stop, that's it, okay? If a person stop, okay? So autonomous driving, they have plenty of this software, plenty of these conditions that not learnable, okay? So they code it with the classical code, okay? But still, we know that everything can be learned. How we know it? Because our brain learned. Okay, our brain is a neural network. Okay, very sophisticated, and we know that it can be solved, and we call it end to end. So solved by neural networks. So that program can be completely written by a neural network. So you give it an input, and she knows what to do. Actually, she knows how to open, how to not. All of this stuff. So we know that any problem can be solved end to end. Okay. So there is this huge discussion whether we should go end to end, when we should go to end to end. Okay. Then there is this deep learning. What is okay? I didn't tell that, but you heard about deep learning. Is mostly in human words. It's a pattern recognition. It's kind of a sensory we have. Okay. So. Deep learning is not an answer to the intelligence. It's not okay. Maybe it's not, but it's still a discussion. But it's not. We know that it's a sensory. We understood how our vision works now. Okay, part of the cortex in a brain that let's say. So we understand that how to teach a machine to learn the same task as our visual cortex does. Okay. So I see deep learning as a very powerful tool that can learn different stuff, but it's not an answer to the intelligence. It's not a general intelligence. Probably it will be a kind of a sensory, so we have to work more and build something even new, something we don't know that will actually do a general intelligence. So. Okay, there is also a discussion whether is it doable or not doable. What is general intelligence by itself? Whether we are general intelligent. We are not. We are special intelligent. Because what is intelligence? I like the definition. There is no definition, but every scientist has given a definition of intelligence. So what is intelligence? Yes? Finish. Okay. Well, I finish with this. What is it? I like this definition, is a capability to generalize on environment. Okay, you give that environment, and you know how to deal with that. You know how to deal with this. You all know how to. So, and that's a good point. If you have a bad environment in your company, no intelligence. I'm sorry. That's it.